to start talking about number theory in this session. So the last session was the last one on graph theory. And as we always do in this course, we first use stuff and then we come back and try to define them. So we've used the integers all throughout this course, and now I'm going to introduce the set of integers to you, and I'm going to say what the set Z actually means. So we've used Z, the set of integers, which means natural numbers and also negative numbers, without actually providing a definition. But we've already seen a definition for the set of natural numbers. So we've seen Peano's axioms, which define natural numbers. So I'm just going to build upon them to define the set of integers. So Z is the set of integers. And this is a rule-based definition. So I'm just going to give you two rules that would create the set Z. And basically anything that you can create using these two rules will be a member of Z. So rule number one says that N is a subset of Z. Or another way of writing this is that if I have something that is in the set N, then that thing is also in the set Z. Okay, so every natural number is an integer. Now, my second rule is the rule that I'm going to use in order to create negative numbers. I'm going to say, if I have some number N, which is a natural number, but is not 0, then there is another number, which I call minus N, which is going to be in Z. Okay, so these are my two rules. And this minus N, this is kind of like a successor of N that we had in the definition of natural numbers. It's just a function that is applied to N. So if I have a natural number N, I have an integer which is minus N. And I'm not applying that to 0 because I don't want to have minus 0 in my set. Okay. Now we can extend all sorts of things that we've seen for natural numbers to the real numbers. So for example, I can define an order. Sorry, not to real numbers, to integers. I'm getting ahead of myself. We will define real numbers at some point. So I can define an order. Remember, on natural numbers, we had an order when we said like A is less than B, right? So I can just say that I'm going to extend the order for natural numbers. So this is going to be an extension of the order I had on natural numbers. Okay. So what is the extension? Basically, if I want to compare two integers, and if both of them are natural numbers, I say use the comparison that you already know for natural numbers. Okay. So I say if A and B are natural numbers, then A is less than B as integers, if and only if A is less than B as natural numbers. Okay, I don't even need to really write this. I'm just extending this, right? Okay, then I need a way to compare negative numbers and positive numbers, and also to compare them to 0, right? For that part, it's pretty easy. I say for every A and B that are natural numbers, and here it's also for every A and B that are natural numbers, I say minus A is less than 0, and that's less than B. So all the negative numbers are less than 0. All the positive numbers are greater than 0. Okay. At this point, I know how to compare two positive numbers because I already had the comparison in N. I know how to compare everything with 0. I know how to compare a negative number with a positive number. Negative numbers are always smaller. I have to also define how I can compare two negative numbers. Right. So here's the thing. So let's say I take two natural numbers, A and B, and I want to compare minus A and minus B. How can I do this? Well, I can define it like this. I can say minus A is less than minus B if and only if A is bigger than B. Right? Or I can write it like this. B is less than B. So now I have an order that can compare any number in the set Z, any integer with any integer. Okay. Now I can continue building upon these extensions. So when I was talking about natural numbers, I had this idea of a successor and a predecessor. Remember, so successor of n was the number after n, and the predecessor was the number before n, right? And the idea was that basically A is a successor of B if and only if B is a predecessor of A, right? And we also showed uniqueness, so we can say the successor and the predecessor. Now, we want to extend these ideas here as well. So let's say I want to extend the idea of predecessor. Okay. So what is predecessor? Again, predecessor is a function P from Z to Z. But I already had a predecessor function when I was talking about natural numbers. And if you remember that, that was, I call it P sub n, which map natural numbers except for 0 to natural numbers, right? So when I was talking about natural numbers, every number had a predecessor except for 0. 0 didn't have a predecessor. And if you remember, we had this idea that for every two numbers A and B, for every two natural numbers A and B, A is the successor of B if and only if B is the predecessor of A. So I want to extend this concept of predecessor so that I can have similar things. Okay. Again, I'm going to have rules. My first rule is going to say for every natural number A that is not 0, predecessor of A is just whatever it was when we were working with natural numbers, right? So predecessor of 2 is 1, predecessor of 5 is 4. So now I have to define the predecessor of 0. What is the predecessor of 0? It's going to be -1, right? So this is my second rule for predecessor. I just say predecessor of 0 is -1. Or if I want to be much more exact about this, this is minus successor of 0, right? Because 1 was actually successor of 0. Okay. Now I have my predecessors for my positive numbers. I have my predecessor for 0. I have to define predecessors for negative numbers. So this is my third rule. I want to say for every natural number A, which is not 0, what is the predecessor of -A? So I want to say something like this, right? I want to say this is -A plus 1. But I can just use the same way that I defined this here. I can say this is minus the successor of A. Okay. Because A plus 1 was successor of A. And now that I have extended predecessor, I can also extend the successor function. Just use this, right? Successor and predecessor are opposite functions. Okay. I'm not going to write that one, but basically you can write rules for successor as well. Now I can also extend the other operations I had. I can extend addition. Okay. What were the rules I had for addition? My first rule was that for every number A plus 0 is A. I'm going to keep this one, right? And I'm going to say now this holds for every integer. I want to define A plus B, right? So this is just going to be the successor of A plus predecessor of B. So basically, if I can find A plus predecessor of B, I can then find A plus.
because B is in that number, so maybe it can't have 3%.
Yes, so I have to say B is not 0. So I know how to add 0 to a number. I know how to add a positive number to some number A. Now I want to say how to add a negative number. So for every A in Z and for every B in N not 0, what is A plus minus B? Now here, I should not use predecessor of minus B, because this will give me a non-terminating definition, right? So if I do that, it would be like, I want to find A plus minus 1, but then I should find A plus minus 2 and add 1, but then I should find A plus minus 3. And so I don't want to do that. I want to somehow get it back to the case where it's 0. So I have an inductive definition here. I want it to get back to this base case. Okay. So what is this? A plus minus B. I can do like this. I can say this is the predecessor of A plus successor of minus B. So basically now I have two different rules, but at the end of the day, the idea is that if you want to find A plus B, try to change it little by little so that B becomes 0. And of course, if B is positive, you have to decrease B. And if B is negative, you have to increase B. Okay. So this is addition. Finally, I can go to multiplication. I was doing multiplication while thinking I was doing addition. Okay. Here again, the idea is very similar. If I multiply something by 0, so for every A in Z, A times 0 is going to be 0. Right. Now, if I multiply by a positive number, so for every A in Z and every B, I want A times B. I can first say take A times the predecessor of B and add A. Okay. And then for the other case, if I want A times minus B, what can I do? I can say first do A times the successor of minus B and then subtract A. Right? But I don't have subtraction.
Yeah.
Right. So I can write it like this. I can write plus minus A. Great. So now I have multiplication. Well, now that we're at it, let's just define subtraction too. Subtraction is pretty easy. I just say that whenever I write A minus B, what I mean is A plus minus B, right? But this works only if B is a positive number. So I have to have another rule for the other case. So if I write A minus minus B, what I mean is just A plus B. Okay. So subtraction is also easy to define. Great. Now I did all of this because I want to define division. Division is the important thing that we want to talk about. Okay, this is division. Oh, by the way, before doing that, I can also do absolute value, right? While I'm at it, I can just define the absolute value. I can say the absolute value of 0 is 0. For every natural number n, the absolute value of n is just n itself. And for every positive number n, the absolute value of minus n is also n. So absolute value is also a function. It's just a function that maps from Z to Z. Or you can also think of it as mapping from Z to N. Okay. Great. Now I have absolute value. Finally, I want to talk about division. Now, the thing about division is that generally when you divide two numbers, first of all, of course, you cannot divide by 0, but then when you divide two numbers, you're going to have a quotient and you're going to have a remainder. So I'm going to say this as a theorem. So this is what I want for my division. I want to say if I have two integers a and b, so let a and b be integers, and let's say I want to divide by a positive number. I want to divide a by b. So for now, let's say b is greater than 0. Then I want to say this. I want to say there exist unique numbers. And from now on, whenever I'm talking about numbers, I'm talking about integers. There exist unique numbers q and r such that a is q times b plus r, and r is smaller than b, but greater than or equal to 0. So what am I saying? I have two numbers a and b. I want to divide a by b. I'm saying I can write a as q times b, so q is the quotient, plus some remainder. And the remainder should be less than b. Okay. But importantly, I'm also claiming that this is unique. There's only one way to find q and r such that this equation is satisfied. Okay. So let's forget about the uniqueness first. Let's prove that we can do this. Let's prove that there is a solution. Why is that hard? Because I want my remainder to be smaller than b. Okay. So how do I find a solution to this? Well, I can rewrite this, right? So I can say, what is my r? My r is basically a minus qb. And I want this r to be as small as possible. So I'm going to create the set of all the possible values for r, and then I'm going to say, take the smallest elements. Okay, so I'm going to say, let a be this set, be the set of all the values that are of the form a minus qb for any q in Z. Okay. But the problem is that if I do this, this A would be a subset of Z, right? And I've already lost some things when I go from N to Z. And one of the main things that I have lost is well ordering. Remember, if I had a non-empty subset of natural numbers, I could say that there is a minimum element, right? But here, I cannot do that. There are many non-empty subsets of Z that don't have a minimum element, right? So I want to somehow make this A to be a subset of N. So I say, only take the values that are non-negative. So A minus QB should be greater than or equal to 0. Okay. Now this A is a subset of the natural numbers. I want to use well ordering. I want to say that this A has a minimum element. But in order to use well ordering, I need something else. I also need to say that A is non-empty. Okay, why is A non-empty? So suppose that I put Q to be 0, then I'll get A. So if A itself is non-negative, then this A is non-empty. But what if A is negative? You see, this is the problem in number theory. Usually things that are trivial are not trivial. Yes, you have to make Q really negative so that Q times B is bigger than A. But we don't know that that's actually possible. So I need to do a lemma here. This is my lemma. I want to say that for every A and B in Z, where B is greater than 0, there exists a Q in Z such that Q times B is bigger than A. Okay, so first case, if A is negative, then use Q equal to 0. Right. Then if A is 0, use Q1. Okay. The interesting case is when A is greater than 0. If A is greater than 0, what should I do? Yes. Okay, yeah, use A plus 1. Okay. And then we can just follow the lemmas that we proved for natural numbers that show that these things work. Okay, so coming back to our main theorem, so this was just a lemma on the side. We're going back to our main theorem. Remember, I have A and B. I want to show that I can write A as QB plus R, where R is between 0 and B. I decided that, okay, R is A minus QB. So let's look at all the numbers that can be written in this form, in the form A minus QB. This is a subset of natural numbers. Because of this lemma, it's a non-empty subset of natural numbers. So now it has a minimum element. And I'm going to take its minimum element. So I'm going to say, let's call it something. R star be the minimum element of A. And again, this exists because of well ordering. Okay. What do I know? I know that R star can be written in this form. So there exists a Q star such that A is B times Q star plus R star. Okay. But I want to prove that this R star is between 0 and B. Okay. So R star is definitely greater than or equal to 0 because I picked it from this set A, and A was a subset of natural numbers, right? So I only have non-negative remainders. But why is it less than B? So I prove this by contradiction. I say, suppose R star is bigger than B. Okay. What can I do now?
Minus 1.
Yes. So I can say, well, A is also B times Q star plus 1 plus R star minus B. Right. So this means that this R star minus B is also in the set A. But R star was supposed to be the smallest element in the set A. So this is a contradiction. Basically, what I'm saying is consider all the possible remainders, all the possible non-negative remainders, and take the smallest one. That's R star. If it's bigger than B, I can create an even smaller non-negative remainder. And so this proves that this is in A. This contradiction proves that R star should be less than B. Okay. Actually, it works if it's greater than B. Okay. Great. So up until this point, we've proven that there is a solution. That if I give you A and B, you can write A as QB plus R, where R is between 0 and B. Okay, less than B. But now we want to prove uniqueness. Why are these unique? Why can't I have two solutions? Okay, so let's do this. This is the uniqueness part. Again, I'm going to say, suppose this is not the case. Suppose I have two different solutions. So let's A Q1B plus R1 and A equal to Q2B plus R2 be two different solutions. Can I have R1 equal to R2? Yeah. So that's the first thing. If R1 is equal to R2, it's easy to verify that Q1 is equal to Q2, which means that these are not two different solutions. There is just one solution.
We have to do the calculation of
Yeah, that's very easy. You can prove that by induction. It's the same as the theorems we had for natural numbers. Okay. So if R1 is equal to R2, then Q1 is equal to Q2, and there are not two different solutions anymore. That's a contradiction. Okay. So R1 is not equal to R2. Okay. And also Q1 is not equal to Q2. Where's the contradiction here? And remember, these are solutions, so R1 is going to be between 0 and B, and R2 is also going to be between 0 and B. The difference between Q1B and Q2B should be the same as the difference between R1 and R2, right? So if I just write everything like this, the absolute value of Q1 minus Q2 times B is the absolute value of R1 minus R2. Now, another thing that you have to prove on your own, another lemma, is that absolute value of A times B is greater than or equal to the absolute value of B. Okay, so if I have two things that are multiplied and I take their absolute value, that's going to be at least the absolute value of each of them. That's, again, a simple lemma that you can prove by induction. So this side is actually greater than or equal to the absolute value of B, which in this case is B itself, because B was a positive. Okay. But what about this one? R1 minus R2. Yeah, these are both numbers that are less than B, so their difference is also less than B. So B cannot be less than B, that's a contradiction. So we have a unique solution. Okay. But here I proved this for the case where B is greater than 0. But honestly, you can also divide by numbers that are less than 0. You just can't divide by 0. Right? So I can actually extend this, and the extension is going to have the exact same proof, so I'm not going to write it. It's just that you do a casework. You say, if B is positive, here's the proof. If B is negative, again, you repeat the same thing, just keeping track that it's negative. So in general, I can say something like this. I can say for every two numbers, A and B, where B is not 0, there exist unique numbers Q and R such that A is B times Q plus R, and R is between 0 and the absolute value of B. Okay. So that's the only thing I have to do when I'm dividing by a negative number. I have to say that the remainder is between 0 and the absolute value of this. And everything else goes through, the proof is exactly the same. Okay, so now we have division, and more importantly, I know that whenever I do division, I get a unique quotient and a unique remainder. Okay. So based on this, I can define divisibility. Okay, so here's the definition. If there exists a Q such that A is B times Q. Okay, so basically I'm saying that A is a multiple of B. B is a divisor of A. Okay. So this is not exactly the same as before, because by this definition, 0 is a multiple of 0 and 0 is a divisor of 0 and so on, but we didn't really have division by 0 here, right? So generally, when I say B divides A, I mean that A is a multiple of B. So we use this definition. There exists some Q such that A is B times Q. Okay, so we can talk about some properties of division. Let's see. Okay, let's go through this really fast. This is theorem 2.2 in the book. And honestly, it's pretty trivial, so I don't want to spend too much time on it. So for every integer a, b, c, we have the following. The first thing is a divides 0, right? Because a times 0 is 0. So 0 is a multiple of a, no matter what a is. 1 divides a, because 1 times a is a, right? And a divides a, because a times 1 is a. So very simple. The second property is this. A divides 1 if and only if a is either 1 or minus 1. Again, you can easily check this. You can use the absolute value rule for this. Now, this one is nice. If A divides B and C divides D, then AC divides BD. Okay. Just write the definition. What does it mean for A to divide B? It means that B is something, let's say M times A, right? And this one means that D is something, let's call that N times C. Okay, so what is BD? BD is M times A times N times C, right? Take the AC to one side, so BD is AC times MN, so BD is AC times something, so AC divides B. And then we have this one. If A divides B and B divides C, then A divides C. This is also pretty easy to prove. Just do the same thing. A divides B, which means that B is something times A. So let's call that M, right? C divides B, so C is something times B. Let's call that N. Okay, so now based on this, I can say that C is NMA, right? So C is something, I don't care what it is, times A. So A is a divisor of C. Another thing, how many did we do? 4, so this is 5, is this. If A divides B and B also divides A, then A is plus or minus B. Again, you can just use the absolute value rule. A divides B, so the absolute value of A is less than or equal to the absolute value of B. And B divides A, so the absolute value of B is less than or equal to the absolute value of A, so their absolute values should be the same. So the only case is that A is either B or minus B. Okay. And then there is this one, which is what we're going to use a lot. So suppose that A divides B and A also divides C. Then A will divide AX plus CY for every X and Y. So I have two numbers that are multiples of A, both B and C are multiples of A. I'm saying I can take any linear combination of B and C. I don't know why I wrote A, B and C, and A divides that. Okay. Actually, what I wrote would be correct too, but not what I wanted to write. Okay. Again, very easy, just follow the definitions, write it like this, and you'll see that this is multiple. Now that we have the concept of division and divisors, we can talk about the greatest common divisor, which is actually going to be what we build almost all of our theory upon. So at this point, you might expect that I would just define prime numbers and talk about, well, every number is a product of primes, but no, GCD comes first. So this is the greatest common divisor. I say this, I say, suppose A and B are natural numbers, sorry, are integers, and not both of them are 0. And not both are 0. I want to define the greatest common divisor of A and B. We say that D, and I want this D to be a natural number, is the greatest common divisor, or just GCD, of A and B if it satisfies the following conditions. Well, the first condition is that, of course, I want D to be a divisor of both A and B. So my first condition is that D divides A and D divides B. And it's in the name, it's a common divisor, right? But I want it to also be the greatest common divisor. So the second condition is that if there is some other common divisor, so for every other D prime, such that D prime is a divisor of A and D prime is a divisor of B, I want D prime to be less than or equal to D. Okay, so I want D to be, as it's the name, the greatest common divisor. Okay, but I'm going to change this definition a little bit, and this is going to look weird to you, but I'm going to say this. I'm going to say if there is any other number D prime that is a divisor of both A and B, then D prime should be a divisor. Should not only be less than or equal to D, it should be a divisor of D. Okay. Now we will see very soon that this is actually the same definition. It doesn't matter if you say it should be a divisor or it should be less than or equal, but I want to go with this definition. Now, if I went with the previous definition, my life would be so much easier, right? So if I go with this definition, I can be sure that the greatest common divisor exists, right? Because, look, I can look at the set of all divisors of A, I can look at the set of all divisors of B. I can take the intersection of these two sets, that's going to be the common divisors of A and B. But then I'm saying I'm only looking at the non-negative ones. right? So I'll just take the non-negative chunk of the common divisors, right? And then I say, just take the biggest element in there. And that's going to be my greatest common divisor. And there is going to be a biggest element because all these elements are at most absolute value of A or absolute value of A, right? But I don't want to do this. And by the way, this also shows you why I'm saying not both of them are zero. Because if both A and B are zero, then every number is a common divisor of A and B, because every number is a divisor of zero. So it's very important that we say not both of them are zero. So with this definition, I can be sure that the greatest common divisor exists. But I'm not going to use this definition. I'm going to use the definition that uses divisibility. So with this definition, I don't even know if such a D exists. It might be that D does not exist at all. Right. So I have to actually prove that this kind of D exists. But of course, if I prove that the D exists with this definition, this same D will satisfy the previous definition as well. Because if D prime divides D, then the absolute value of D prime is less than or equal to the absolute value of D. And since D was non-negative, then D prime is less than or equal to D. Okay. Great. So this is the next theorem that I want to prove. And this next theorem is actually going to do something amazing. It's going to show not only the greatest common divisor exists, but it's going to give us kind of a formula for how it looks like. Okay. So I want to say for every natural numbers A and B in Z, where not both of them are zero, not both zero, I want to say that this D exists, this GCD exists, and I want to say something more. I want to say there exist two numbers X and Y such that the GCD of A and B is AX plus BY. So this is what I want to prove. So I'm not only claiming that the GCD exists, I'm even claiming that the GCD can be written as a linear combination of the two numbers, A and B. So I can multiply A by something, let's call it X, and then I can multiply B by something else, and I can add them together, and that's going to give me the GCD. Okay. Here's our proof. Well, again, I'm going to do the same thing that I did when I was defining division. I'm going to say, look at all the numbers that are of this form and only keep the non-negative one. So if you have a number that is of this form and it's negative, throw it out. Just keep the numbers that are of this form and are non-negative. Okay, or actually that are positive, let's say. Yeah, I don't even want to have zero there. So let's only keep the numbers of this form that are positive. That's going to give me a set that is a subset of natural numbers. So it's going to have a minimum element because we have well ordering in the natural numbers. And then I'm going to say, take this minimum element, that's your GCD. And it's going to have all the properties that I wanted to have. It's going to have all of these properties. Okay. So I'm going to define A, again, the set A, as the set of all D such that D is greater than 0 and there exists X and Y where D is AX plus BY. So I'm taking all the numbers that are a linear combination of A and B and are also greater than 0. I'm calling that set A. And then I'm going to say, well, this set A is a subset of natural numbers, right? Because I said that all of the elements should be greater than 0. Why is it non-empty? because if I look at A, either A or minus A is going to be in this set. And either B or minus B is going to be in this set too. And I said not both of them are zero. So at least one of them is not zero. And if it's positive, then it's in this set. If it's negative, then it's minus is in this set, right? So this is a subset of the natural numbers, and it's not the empty set. So A has a minimum element. Let's call that minimum element also D. Okay. So I claim that D has all the properties of the greatest common divisor. Okay. First of all, for my greatest common divisor, I need it to be a natural number, and it is a natural number because A is a subset of natural numbers. Okay. Does D divide both A and B? So what do I know? I know that D is AX plus BY, right? And what I hope to prove is that D is a divisor of A. So suppose D is not a divisor of A. What happens then? What if D is not a divisor of A? Because I want to prove this by contradiction. I want to prove that D is a divisor of A, right? So I want to prove that D divides A. So suppose that it doesn't. Suppose D does not divide A. What does this give me? So I can write A as Q times D plus R, where R is less than D and greater than 0, right? A is QD plus R. Now what can I do? I can say that, well, A is Q times, instead of D, I can put AX plus BY plus R. Okay. But what can I do now? I can write R as a linear combination of A and B, right? So R is going to be A minus QAX minus QBY. Right? Or if I want to really get this together, I would say A times 1 minus QX plus B times minus QY. So I could write R as a linear combination of A and B. But R is greater than 0, and it's also less than D. That's a contradiction with the definition of D. D was supposed to be the smallest number that can be written as a combination of A and B, right? So this is a contradiction. Where did this contradiction come from? It came from this assumption that D does not divide A. So this proves that D divides A. Okay. So D divides A. Okay. But I can do the exact same proof for B. I can show exactly in the same way that D divides B. Right? Just repeat the same thing, just on the B side. So far, we have proven that D divides A and D divides B, which is great. Right? So we've so far proven that D is a common divisor of both A and B. Now, so we have proven this part and we have proven this part. We just have to prove that if I have any other number that is a divisor of A and a divisor of B, then it's also a divisor of D. Okay. So here's the thing. Suppose that I have some D prime, and this D prime is a divisor of A, and it's also a divisor of B. But what do I know about my number D? I know that it was the smallest element in this set, and this was the set of all the numbers that could be written as a linear combination of A and B. So D is a linear combination of A and B. D is of this form, AX plus BY, right? So D is AX plus BY. D prime divides A, so D prime divides AX. D prime divides B, so D prime divides BY. So D prime divides AX plus BY, so D prime divides D. Right? So this part is a multiple of D prime. This part is also a multiple of D prime, so the sum should also be a multiple of D prime. Okay, great. So we proved the second part. So we proved all of it. So if A and B are integers and not both of them are 0, there is a greatest common divisor with this definition. So it divides A, it divides B, and if there is any other number that is a common divisor of A and B, then it's a divisor of the greatest common divisor. And not only that, but we also know that we can write the greatest common divisor as a linear combination of A and B. Okay, great. So now we can, if we want, we can go back to the previous definition, and here instead of divides, we can put less than or equal, and you can easily see that these two things are the same. By the way, we kind of proved something else as well. If you look at this set A, the set of all the numbers that can be written as a linear combination of A and B, we just proved that this set is exactly the set of the multiples of the GCD. Right? So what did I do here? I said whenever I have some number that is of the form AX plus BY, it's a multiple of my GCD. Right? So I can do this corollary here. I can say for every A and B, where not both of them are 0, not both A and B are 0, if I look at the set of all the numbers that are of the form AX plus BY, this is just going to be the multiples of the GCD. Sum Q times GCD of AB. Q. These two sets are the same. So we have another definition here. I'm going to define relatively prime before I define prime itself. So relatively prime is this. We say two numbers A and B are relatively prime if their greatest common divisor is 1. Okay. We say A is relatively prime to B, and we write it like this. If the GCD of A and B is 1, which immediately gives us another way of defining relatively prime. I can say that A is relatively prime to B if and only if there exist two numbers X and Y such that AX plus BY is equal to. So you can use whichever definition you want for relatively prime, but let me just give you another result here, which is kind of interesting as well. This is a simple theorem. So I want to say this. I want to say if GCD of A and B is D, then GCD of A over D and B over D is 1. And by the way, I'm using division here, but this is still working with integers because I know that D is a divisor of A. So A over D is going to be just another integer. I can use division. Just write the definition, right? GCD of A and B is D. So that means that there exist some numbers X and Y such that A times X plus B times Y is D. Okay. So now use the same X and Y, but use them on A over D and B over D. So what is A over D times X plus B over D times y. This is just 1, right? So I could find a linear combination of these two numbers that summed up to 1. So the GCD of these two numbers is 1. Actually, the only really hard part of this theorem is that you have to realize A over D is an integer, right? But that's by definition, because D was the greatest common divisor of A and B, so it's a divisor of A. So A over D is an integer. Here's another theorem. I want to say this. Suppose that A divides C and B also divides C. So A divides C and B divides C as well. And suppose that A and B are relatively prime. Then A times B divides C. Now, all of you have this idea in your mind that, well, if only I could just say, let's look at the prime factorization of A and the prime factorization of B, right? So what is this theorem saying in terms of prime factorizations? It's saying that, well, A divides C, so the power of every prime in A is less than or equal to the power of the same prime in C. And the same thing between B and C. And then A is relatively prime to B, so they don't have any common prime factors. So their multiplication should also divide C. So it would be super easy to prove this if we already had the fundamental theorem of arithmetic, which says that every number is a multiplication of prime numbers, product of prime numbers, but we don't have that yet. Okay. So you have to prove this with what we have so far. Okay, what do I want to show? I want to show that A times B is a divisor of C. So I want to somehow rewrite C in the format of some other number times A times B, right? But what do I know? I know that A divides C and B divides C. And I know that A and B are relatively prime. So let's try to write these things out. So A and B are relatively prime. That means that there exists some x and y such that A times x plus B times y is equal to 1. Okay. But now I want to somehow get that C is equal to something. How can I introduce C here? Let's just try multiplying both sides by C. Okay. So what will I get? I will get that C is A times X times C plus B times Y times C. Okay. Is this helping me? Am I on the right track? What do I want? I want to show that C is A times B times something. So I want to somehow create A times B here, right? But in this term, I have A. In this term, I have B. But I also have C in both of them. So maybe I can use that C to somehow get a B on this side and use this C to somehow get an A on this side. Okay, how can I do that? Using what I already know here. So I know that A divides C. So let's say that means that C is A times some M. And B divides C. So let's say C is B times something else times N. Okay, so now I can rewrite what I had here. I can say C is A times X. And instead of this C, I'm just going to put B times N. Right? Plus B times Y. And then instead of this C, I'm going to put A times N. Okay. So now I finally have the A-B terms that I was looking for. So I can say C is A times B times, on this side I have Xn, on this side I have Ym. Okay, I don't care about what's in the parentheses. What I care is that C is now A times B times some other number. So A times B divides C. Okay. So we proved our theorem. And we proved our theorem without talking about prime numbers. Okay. Now I want to do another theorem which is actually very important, and this is called Euclid's lemma. It's called the lemma, but it's super important. Again, this is something where you would be easily able to prove it if you had the fundamental theorem, but you don't have it yet. So it says this. It says if A divides BC, and if the GCD of A and B is 1, GCD of A and B is 1, or in other words, A is co-prime with B, then A must divide C. Again, with the fundamental theorem of arithmetic, this is trivial. But we don't have it. So how would you prove this? Just try to prove this and remember the previous proofs that we had. It's like trying to rewrite things. So I want to do something similar to here. What I did here was that I was rewriting C, and I got C to be A times B times something else. I want to get something similar here. Instead, I don't have A times B, I just have A. So I want to show that C can be written as A times some other number. Okay. Let's do this. I know that GCD of A and B is 1. So there exists some X and Y such that AX plus BY is equal to 1. How do I get C? Just multiply both sides by C. So CAX plus CBY is equal to C. But I want to show that C is a multiple of A. So I want to show that the left-hand side is a multiple of A. Okay. I don't have a problem with this term because it already has an A in it. This one is definitely a multiple of A. But look at this one. This one has BC in it, and I was assuming that A is a divisor of BC. So this one is also a multiple of A. So C has to be a multiple of A. Okay. So A divides CAX because it has A in it, of course. And then because A divides BC, then A divides BCY. So A divides the sum of them. A divides CAX plus CBY, which is just C. Okay. Great. So let's just get the intuition behind this. I'm saying that if A divides B times C and A and B are relatively prime, the reason that A is dividing B times C only has to do with C. It's because A divides C. Okay. Again, if we could look at the prime factorization of these numbers, which is what we're going to see in the afternoon, I could say, look, A divides B times C. So if I look at the power of any prime number in the factorization of A, it's going to be less than or equal to the power of the same prime number in the factorization of B times C. But then when I say A and B are co-prime, it means that they don't have any prime numbers in common. So any prime number that appears in A with some power has to appear in C with the same power or higher. That's what this theorem is effectively saying. But again, we're doing it without talking about factorization into primes. We haven't even defined primes yet. That's going to be the next session.